Hi there. So this session or this video is rather a bonus sort of video. So if you just want to study or confine yourself to a syllabus and study these laws, then you can kind of skip this video. But if you really want to know why these laws work and the intuition behind these laws, then I suggest you stay hooked till the end. Now, the laws like linear propagation of light and reflection of light, sin I equal to sin r, angle of incidence equal to angle of reflection, and the law of refraction that sin I upon sin r is a constant. But these are generally taught as laws, okay, in the school. So you can't really know why this is true. Now, I also had this experience, right? When I remember 8th standard, so 2 years ago, there was in a hall. We were in a hall studying light. We were drawing concave mirrors, image formation. And then what happened was there was a student. She was in class 12th at that time, I remember, not too clearly. And I asked her, okay, they are telling me that angle of incidence equals angle of reflection, but why is this true? And is this necessarily true? Now, those who heard me were like, they were not too comfortable with this question, and they find out that this was a very strange question. And she replied, no, I wasn't really satisfied with the reply. She said that's is just a property of light, so it is just, And now that I know why this is true, let me explain it to you using one principle. Okay, there's one principle that governs almost everything which we study, which is Fermat's principle of least time. Big name, right? Now it turns out it's not so complicated idea. It just says that when light travels from a point to another point, it takes the path which it can cover in the shortest time. Now I want you to pay attention to the word shortest time, not the shortest path, but the path it can cover in the shortest time. Now, as an analogy, I suggest you imagine like light behaving like humans, okay? So everybody who's watching the video might have stuck in some traffic at least once in a lifetime, okay? Now, when you are stuck in a traffic, and the shortest path is already filled with, other vehicles, cars, buses, you can't really move quickly through the path, right? There's a lot of obstacles in the path. So what do? You go through lanes. The path might be longer, but you will reach your destination in a substantially lesser time. So this is kind of how light behaves, okay? So when such things happen, light also tends to choose the path of the shortest time. Now, why this is true, I think you should just search about this on the net. Let me give you a hint. So this requires your thinking like light traveling as waves, and then you use something called Huygens construction. Then you just go and study about it. So, and let us study an interesting application of this. So say you are in a ground, okay, and the ground is really smooth and everywhere it's same everywhere. Okay, so let's just draw it. So here's the ground, okay, there, and say you're standing here and you want to go here, okay, in the shortest time. How would you go about it? Well, if every direction is the same and there are no obstacles between them, then you would travel some sort of this path, right? The shortest path. And what is the shortest path between 2 points? A line, right? You would travel in a straight line. Similarly, a light does something similar. Now, instead of grounds, light travels medium, okay, different mediums. Now, if the medium is similar everywhere, we call such a medium homogeneous isotropic medium. Okay. Now, if light, say, wants to travel from this point, let us call it, source S to another point, how will it go? Well, if all the paths it can take are identical, right? This path length, why would it bend? Right? Because there are no obstacles, so light wouldn't really bend. It would just go in a straight path. between if the medium is homogeneous and isotropic, then light will travel in a straight path. And what have we just proved? We have proved the phenomena of rectilinear propagation of light using our understanding of Fermat's principle of least time. And the interesting thing is that Fermat's principle of least time extends to different media as well. How? Let us see it using an analogy. Imagine you're on a beach, and this is a very classic example, by the way. Now you're walking and you see a guy who is drowning, so he needs help. This is the best drawing of my stick figures, okay? So pardon me with that. Now you want to save him or her, and how would you go about it? Now if you're really enthusiastic, you might go like this side somewhere here, and you might go like there in this direction, okay? Now think about it. So if a person is drowning in water and you're walking on land, well, most people run faster on land than they can swim in water. Now if you take this path, okay, what else can you do? If you think about it, you need what do you want when you save somebody? Do you need the quickest, shortest path, or you need the quickest path? Which path will you choose? Of course, right, you need the quickest path. And if your speeds are different, so your speed is different in land and different in water. So this speed in land is greater than your speed in water. Okay. Now you can't. The straight line is no longer the path of quickest time. Why? Because you are traveling a considerable amount of distance in water. Therefore it will slow you down. Now how can you go about doing this? Now if you take a path which goes something like this, so you travel a longer distance on land, okay, now consider longer distance, and then you bend to save this guy. Okay, now what are you doing? You are traveling longer in a medium in which your velocity or a speed is larger, and you are traveling a lot lesser in the medium in which your velocity is slower. Your speed is less. What will happen now? See, if this length, if you are traveling a lot longer in water, then obviously you will reach this point, you will reach the guy much slower. Now this and another thing you can do is you can go like there and then go something like that, okay? Now which path you should prefer? Path A, path B, or path C? But it turns out that you cannot choose path A because it takes time again. What about path C? What happens is that this time again it's longer because you are traveling a lot longer distance in land. You need a trade-off between these. You choose path B. So what do you do? So again, let me just simplify this drawing. You are here and this is the land-water interface, and you want to save this guy. You do something like this. You bend a little bit inward, and then you go save that guy. This is the most efficient path because it's the path of least time. Now how would light behave? Light also behaves in some sort of similar manner. See, so if you have an interface, okay, there is this medium 1, it is M1, and this medium is M2, okay. Now you need to, so say there is light source, okay, and then you need to go to this point right over there. Now will light take the direct distance? No, right? Because what does light want? Light wants to travel as quickly as possible. And which path among these three was the fastest path? Path B, right? So it must trace something similar to path B. So it might go something like there and then here. Okay, something similar. Now this is what light does. Okay, that's what you can conclude, because if light travels faster in medium 1, light travels faster in medium 1 than medium 2, it must stay in medium 1 for a longer interval of time than it stays in medium 2. Now, this is how you save a person, and this phenomena of light bending when the mediums M1 and M2 in this case have different velocities. This phenomena is called refraction of light, and we'll study refraction in a great detail after a few videos. Now, till now, I hope you have understood the Fermat's principle of least time in a very simple manner, and see you next time.